Now let's say if we have two hydrogen atoms, and if these two hydrogen atoms approach each other, what's going to happen? As you know, they will react and form a covalent bond. And a covalent bond is basically a bond where the electrons are being shared. And so you can write the bond with a single bond, or you can put two electrons between the hydrogen atoms. And this concept makes sense if you think of electrons as particles. But what happens if you begin to think of electrons as waves? In that case, a covalent bond is formed from the overlap of atomic orbitals. And an orbital is a region where electrons are located, where you have a high probability of finding an electron. So let's think of electrons as waves. If we have two waves in phase with each other, what's going to happen? They will interfere constructively to create a bigger wave with a larger amplitude. So if you have two atoms approaching each other, and if their orbitals are in phase with each other, they will overlap constructively, and so you're going to get a bond, particularly a covalent bond, because the electrons are being shared. But what happens if the two waves are out of phase with each other? Well, destructive interference will occur, and instead of getting a bond, you're going to get a node, which is a region of zero electron density. So basically, the probability of finding an electron in this region is almost zero. Now, according to valence bond theory, a covalent bond is basically the sharing of electron density between two atoms as a result of the constructive interference of their atomic orbitals. So let's consider hydrogen again. Hydrogen has one valence electron, and the electron configuration of hydrogen is 1s1. An s orbital has a spherical shape. So this is going to be hydrogen with its spherical orbital. And let's react it with another hydrogen atom. So when these two get together, their orbitals will overlap, and you're going to get something that looks like this. And so what we have in the middle is a covalent bond. Whenever two atomic orbitals overlap head to head, it's known as a sigma bond. All single bonds are sigma bonds, so keep that in mind. Now, what about when carbon mixes with hydrogen to create methane? In order to do this, carbon has to hybridize its atomic orbitals. It has to create hybrid atomic orbitals. Now let's talk about the electron configuration of carbon. It's 1s2, 2s2, 2p2. Carbon has a total of 6 electrons. 2 of those electrons in the first energy level are core electrons, and they don't participate in most chemical reactions. The other 4 in the highest energy level are known as valence electrons, and the valence electrons do participate in chemical reactions. So let's draw an energy diagram for a free carbon atom. So we have the 1s level, the 2s level, and the 2p sublevel. So we have 2 electrons in the 1s level, 2 in the 2s, and 2 in the 2p sublevel. This is the ground state electron configuration for carbon. In the excited state, an electron here could jump into this empty orbital if it's given energy. But right now we're going to just talk about the ground state electron configuration. So during hybridization, the 2s orbital and the 3 2p orbitals, they're going to mix together to form a hybrid sp3 orbital. So the 1s level is going to stay the same. Now we're mixing together 4 atomic orbitals, and so we're going to get 4 hybrid orbitals. And they're going to be degenerate orbitals of the same energy. So if we mix an s and 3p orbitals, what are we going to get? We're going to get a hybrid orbital called an sp3 orbital. And because we mixed 4 atomic orbitals, we're going to get 4 sp3 orbitals. Now, what should be the energy level of an sp3 orbital? Should it be close to the 2s level or to the 2p level? What would you say? Because an sp3 orbital is produced from mixing 3p orbitals and one s, it has more p character than s character. In fact, it has 25% s character, 75% p character. We have one s out of 4 atomic orbitals, so 1/4 is 25%. We have 3 p orbitals out of 4 atomic orbitals, so 3/4 is 75%. And so, because it's mostly p, the energy level should be close to the 2p sub level, but a little bit lower than it. So we get 4 hybrid orbitals. These are known as degenerate orbitals because they have the same energy level. As a result, we're going to place all 4 electrons equally among those 4 orbitals of equal energy. So the 1s level is unhybridized, it was unaffected. But these 4 atomic orbitals were hybridized into these 4 sp3 hybrid orbitals. And hybridization is basically mixing. If you mix water with orange juice, you're going to get something in the middle. You're going to get a hybrid. Or let's say if you mix orange juice and milk, you're going to get something in between. And that's what hybridization is. You're just mixing atomic orbitals. So if you mix S and P, you get something that's in between S and P. And so these are the 4 hybrid sp3 orbitals. Now let's go back to methane. Methane has 4 single bonds, and so it has 4 sigma bonds. And as we said before, the carbon in methane has 4 sp3 hybrid orbitals highlighted in red. And hydrogen can only form an s orbital because it has 1 electron in its 1s sublevel. So let's say if you have a test question and it asks you, what is the hybridization of the central carbon atom? The hybridization of carbon is sp3. Now, how can we describe the hydrogen orbital? We can say it's simply s. And so if we want to describe the bond that connects carbon and hydrogen, we could say it's a hybrid of s and sp3. Those orbitals in red are sp3 hybridized, and hydrogen is simply an s orbital. So when you mix an s orbital with an sp3 orbital, you could say it's a hybrid of s sp3. So that's how you could describe the hybridization of the bond. And so anytime you have an overlap of atomic orbitals, you're going to have a sigma bond. So this whole thing is 1 sigma bond, this is another, and so methane has 4 sigma bonds, or 4 single bonds, or 4 covalent bonds. You could describe it any of those 3 ways. Now let's talk about ethane, C2H6. How many sigma bonds are in ethane? As we said before, a single bond is a sigma bond. So 1, 2, 3, 4, 5, 6, 7. So we have 7 sigma bonds. Now, what is the hybridization of the carbon atoms in ethane? Like methane, the hybridization of carbon will be sp3. And each hydrogen atom will have an s orbital. So to describe the CH bond, once again, we could say it's a hybrid of s and sp3 atomic orbitals. Now, sometimes you need a simple way to quickly determine the hybridization of carbon. So anytime you see carbon attached to 4 atoms, the hybridization is going to be sp3. If you add up the exponents, 1 plus 3 is 4. Now let's say if you see carbon attached to 3 atoms. Let's say this is X, X, Y, or something. What do you think the hybridization of carbon is going to be? it's going to be sp2. If you add up the exponents, 1 plus 2 is 3. Now let's say if carbon is attached to two elements. Let's say this is N and this is R. Or let's say if it's in this arrangement, like in carbon dioxide. The hybridization of carbon will be sp. If you add 1 plus 1, you get 2. And for hydrogen, you could describe the atomic orbital as s. It's only going to be attached to one thing. So those are some things to keep in mind. Now for those of you who might be studying for the organic chemistry final exam, I have a video that can help you, and it's on my Patreon page. If you go to patreon.com/mathsciencetutor, you can access that page. And if you scroll down, there's a lot of other videos I have here too, but let's say if you're taking the first semester of organic chemistry, I have a 6-hour video that can help you with that if you decide to become a patron. Now, on YouTube, I have a free 2-hour trailer version of this video, but if you want the entire 6-hour video, you can access it here or on Vimeo as well. And for those of you who are taking the second semester of organic chemistry, I have an 8-hour video that you can access as well. And there's some other stuff here that you could find too. If you're taking Gen Chem or physics, I have stuff on that as well. So that's it, just in case you're interested. Now let's work on some practice problems. What is the hybridization of carbon in ethene? Describe the overlap of atomic orbitals of the CH bond and the CC bond in ethene. How many hybrid orbitals are in ethene, and how many unhybridized p orbitals are present? Finally, how many sigma and pi bonds are found in this molecule? Go ahead and try this problem. So let's start with a Lewis structure. So ethene has 2 carbons, and we're going to make this molecule symmetrical, so we're going to put 2 hydrogen atoms on each carbon. Now carbon likes to form 4 bonds, and so right now each carbon atom has 2 bonds. So we need to put a double bond in the middle so that every carbon atom has 4 bonds. So what is the hybridization of carbon in this structure? So focusing on that carbon, we can see that it's attached to 3 other atoms. And so its steric number is 3. So as a result, the hybridization for that carbon is going to be sp2 or s1p2. 1 plus 2 is 3. So this carbon must be sp2 as well. And this hydrogen has an s orbital. So now that we have the hybridization of all of the carbon atoms in ethene, let's talk about the overlap of atomic orbitals of the CH bond. So carbon has an sp2 hybrid orbital, and hydrogen has an s orbital. So the CH bond has an overlap of these 2 orbitals. So you could say it's an sp2 s bond. Now what about the overlap of atomic orbitals for the CC bond? We could describe it as being an sp2-sp2 bond. Now what about the next question? How many hybrid orbitals are in ethene? Well, we said that each carbon atom is sp2 hybridized. To form that hybridization, we need to mix 1 s orbital and 2 p orbitals. Now, when mixing 3 orbitals, you're going to get 3 hybrid orbitals. Carbon has an s orbital and 3 p orbitals. So notice that we've only used 2 of the 3 p orbitals, which means that there's 1 p orbital that didn't participate in the hybridization process. So every carbon atom in this ethene molecule is going to have 3 hybrid sp2 orbitals plus 1 unhybridized p orbital. So if there are 3 hybrid sp2 orbitals and 1 unhybridized p orbital, per carbon atom, and ethene has 2 carbon atoms. So we could say that there's going to be 6 hybrid sp2 orbitals and 2 unhybridized p orbitals. And so this is the answer to the next 2 questions. There's 6 hybrid sp2 orbitals in ethene and 2 unhybridized p orbitals in that molecule. So let's create a visual illustration of what we're talking about here. So during hybridization, we're going to mix an s orbital with 2 p orbitals, and that will give us 3 hybridized sp2 orbitals. Now one of the p orbitals will be unhybridized, so it's going to remain at the same energy as it was before hybridization. Now the sp2 orbital is going to be somewhere between the s orbital and the p orbital. It's 33% s and approximately 67% p. So it has more p character than s character. So let's draw the orbitals of ethene. So this carbon atom has 3 sp2 hybrid orbitals highlighted in red. And the second carbon atom also has 3 hybrid sp2 orbitals. So thus we have a total of 6. 1, 2, 3, 4, 5, 6. So those are the 6 hybrid sp2 orbitals in this molecule. And then we have 4 hydrogen atoms, each with an s orbital. Now what about the unhybridized p orbital? Where is that in this molecule? The unhybridized p orbital exists above and below the sigma bond. The overlap of atomic orbitals produces the sigma bond. But the unhybridized p orbitals, they produce the pi bond. So now we can move on to our next question. How many sigma and pi bonds are found in this molecule? Now keep in mind, every single bond represents a sigma bond, and a double bond represents 1 sigma and 1 pi bond. So if we draw ethene this way, you can easily calculate the number of sigma and pi bonds. So every bond contains a sigma bond, so it's going to be 1, 2, 3, 4, 5. So there's 5 sigma bonds. And every double bond contains 1 pi bond. So because there's only 1 double bond in ethene, there's only 1 pi bond. So this is a sigma bond, that's 1. That's another one, 3, 4, 5. So sigma bonds are created whenever atomic orbitals overlap each other. And so these are all sigma bonds. Now, whenever you have unhybridized p orbitals, you're going to have a pi bond, and it exists above and below the sigma bond. So looking at the CH bond, we saw it's a mixture of an s orbital and an hybrid sp2 orbital. Now, for the pi bond, we described it as an overlap of an sp2 and another sp2 hybrid orbital. Now that's true, but it doesn't describe the whole picture. Because if you look at this particular sigma bond, we do have an sp2 hybrid orbital on the left and on the right. So this only describes the sigma bond in the double bond. It doesn't describe the pi bond. The pi bond is produced by unhybridized p orbitals. So this describes the pi bond, but this describes the sigma bond. So I just want to highlight that important concept. So let's summarize what we talked about. So for the CH bond, we saw that the hybridization of carbon was sp2, and the hydrogen is basically an s orbital. And so the sigma bond of the CH bond, you can describe it as an overlap of an s and an sp2 orbital. Now, for the CC bond, it's a double bond, so it has a sigma and it has a pi bond. Now, the sigma bond in the double bond, you can describe it this way. It's an overlap of an sp2 and another sp2 hybrid orbital. The pi bond, it's based on the two unhybridized p orbitals. Here's another similar problem. So based on the last problem, go ahead and try this one. So let's start by finding the hybridization of carbon in ethine, also known as acetylene. So let's draw the Lewis structure. Each carbon atom is going to have one hydrogen atom. And in order for carbon to have 4 bonds, we need to put a triple bond in the middle. And so that is the Lewis structure for acetylene. Now, let's analyze this carbon. It's attached to 2 other atoms, and so it has a steric number of 2. And so we could say that carbon is sp hybridized. 1 plus 1 is 2, which means this carbon is also sp hybridized. And the hydrogen is basically just s. So now let's describe the overlap of atomic orbitals of the CH bond. So we're going to overlap an sp orbital and an s orbital to create the CH bond. And for the carbon-carbon bond, which is a triple bond, we're going to overlap these 2 orbitals to create the sigma bond that's in ethine. And keep in mind, the pi bond is always formed using unhybridized p orbitals. Now let's jump to the last question. How many sigma and pi bonds are found in this molecule? So just count the bonds. 1, 2, 3. There's going to be 3 sigma bonds. Now we said that a double bond has 1 sigma and 1 pi bond. What about a triple bond? A triple bond has 1 sigma and 2 pi bonds. So this particular molecule has 3 sigma bonds and 2 pi bonds. So that's the answer for the last question. So to summarize, for the CH bond, the sigma bond in it is based on the overlap of an sp2 hybrid orbital and an s orbital. Now for the triple bond, the sigma bond is based on the overlap of 2 sp hybrid orbitals. The pi bond is based on the 2 unhybridized p orbitals, but there's 2 pi bonds. So that indicates that there's a total of 4 unhybridized p orbitals. And that basically answers this question. So we said that each carbon atom is sp hybridized. So to make it, we need to mix an s and a p orbital to get an sp orbital. Now carbon, we know, has 1 s and 3 p orbitals. So if we're using an s and a p to make an sp hybrid orbital, you can see that each carbon atom has 2 unhybridized p orbitals. Since we're mixing 2 orbitals to get the hybrid orbital, there's going to be a total of 2 hybrid sp orbitals, and there's 2 unhybridized p orbitals, and that's per carbon atom. So since there's 2 carbon atoms in ethine, we need to multiply these numbers by 2. So we're going to have a total of 4 hybrid sp orbitals and 4 unhybridized p orbitals. So this is the answer to those 2 questions. So let's draw the energy diagram for carbon. So during hybridization, we're going to mix these two together. And so it's going to be 50% s and 50% p. And so we're going to have two hybrid sp orbitals that's exactly between s and p. And then the other two unhybridized p orbitals will be at their same level. So this is the new energy diagram for carbon in ethine. So here is the two hybrid sp orbitals, and here's the two unhybridized p orbitals per one carbon atom. So now let's draw it. So here's the first hybrid orbital of carbon, and here's the second one. And then for the other carbon, here's the other hybrid orbital, and here it is for the second one. So we have a total of 4 hybrid sp2 orbitals. And then we have the two hydrogen atoms with their s orbitals. So this is a sigma bond. Here's another sigma bond, and that's a sigma bond. So this sigma bond is based on the overlap of an s and an sp2 hybrid orbital. And this sigma bond is based on the overlap of an sp2 and another sp2 hybrid orbital. Now we said that each carbon atom has two unhybridized p orbitals. So this is the first unhybridized p orbital in each carbon. And so this will create one pi bond. Now I'm going to highlight the second unhybridized p orbital, but it's going to be in green. And so that will create another pi bond. So there's a total of 2 pi bonds, the one in green and the one in white. So we have a total of 3 sigma bonds and 2 pi bonds in this molecule. So here's the first sigma bond, this is the second, and this is the third. And then we have 4 hybrid sp2 orbitals, 1, 2, 3, 4. And we also have 4 unhybridized p orbitals. So this is the first one, that's 1. This here is the second one, that's number 2. And this is the third one, 3. And this is the fourth one, 4. So 1, 2, 3, 4. Those are the 4 unhybridized p orbitals. So I want you to understand that. And so that's it for this problem. That's all we can do. Describe the hybridization of every non-hydrogen atom in the molecule shown below. Determine the number of sigma and pi bonds as well. So go ahead and try this. So let's start with the carbon atom. What is the steric number of the carbon atom? The steric number will be the total number of atoms attached to that carbon atom and any lone pairs on it. So it's 1, 2, 3. If the steric number is 3, the hybridization is going to be sp2. If you add 1 and 2, you get 3. So now what about this carbon atom? So this particular carbon atom is attached to 1, 2, 3, 4 other atoms. So it has a steric number of 4. And so the hybridization for that carbon is going to be sp3. 1 plus 3 is 4. Now let's move on to this carbon atom. It has a steric number of 1, 2. And so it's going to be sp hybridized. And this carbon will also be sp hybridized as well. Now what about this one? So it has a steric number of 1, 2, 3, 4. So it's going to be sp3 hybridized. Now what about the nitrogen atom? What is the hybridization of it? So let's determine the steric number. So it's attached to 3 atoms and it has 1 lone pair. So it has a steric number of 4. Therefore, the hybridization for that nitrogen will be sp3. And finally, what about the oxygen? It's attached to a carbon and it has 3 lone pairs. So it has a steric number of 3, and so it's going to be sp2 hybridized. So in a typical exam, if you need to determine the hybridization of an atom, that's a quick and simple method to do so. Now let's determine the number of sigma and pi bonds. So the most efficient way to do that is just to count every bond once. Every bond will contain 1 sigma bond. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So there's going to be 13 sigma bonds. Now what about the pi bonds? Keep in mind every double bond has 1 pi bond. So there's 1 pi bond in the carbon double bonded to an oxygen. And in a carbon-carbon triple bond, there's 2 pi bonds. So therefore we have a total of 3 pi bonds in this molecule. And so that's the answer to the second part of the problem. Number 4. Which of the following represents a hybridized atomic orbital? Select all that apply. So I'm going to list out the hybridized atomic orbitals and the unhybridized atomic orbitals. The unhybridized atomic orbitals, they have just a single type of letter, either S, P, D, or F. So those are the unhybridized atomic orbitals. The hybridized atomic orbitals is basically a blend of 2 or more different types of atomic orbitals. So sp, that's a hybrid of an s and a p orbital. sp2 is a hybrid of an s and 2 p orbitals. sp3 is a hybrid of an s and 3 p orbitals. dsp3, it's a hybrid of a d, an s, and 3 p orbitals. And the last one, d2sp3. So if you see 2 or more different letters, you know you're dealing with a hybrid orbital. If you just see one letter by itself, it's an unhybridized orbital. So hopefully this video helped you to see the difference between a hybridized atomic orbital and an unhybridized atomic orbital. But that's all I got. Thanks for watching.